So yeah, as Kylie said, I'm Leah McGuire. Today I'll be talking to you about types and how wonderful they are for machine learning. So just to give you a little preview of what the talk is going to be about, basically first I'll talk about machine learning at Salesforce and what that actually means, what Salesforce is. Some of the problems that come up when you're doing machine learning in a business-to-business environment as opposed to customer-facing. Then I'll talk about how we solve a lot of those problems using AutoML, so automating a lot of the steps that you do in a typical machine learning workflow. And I will really harp on the utility of types in doing that, so how types help them, how we use them in our automation. And then I'll give a brief summary of what we've learned and where we think we're going with this. So what is Salesforce? Salesforce is essentially a company that stores other companies' data, right? So it's made up of what we call clouds, which are things like sales, service, marketing, social data. Basically, these are entities within Salesforce that are repositories for data for many different companies. So we store data for Uber, we store data for Comcast, Square, UCSF, just a ton of different companies, and we store that data in different categories like sales. We run call service centers. We store social data, so things like tweets from these companies. We also store data for many smaller companies, right? So when you think about machine learning, it's actually a pretty tough problem, right? You have to bring your data in, you have to process it, you have to do ETL, put that into a data warehouse where you can access it. You have to run it through the appropriate algorithms, and you need to then do some DevOps to serve up those answers. And so this process is actually out of reach of many of the smaller companies that we've shown, right? They don't have the data scientists or the data engineers to actually do this. And even for a lot of the larger companies, the sales unit of Uber may not have engineering and data science resources to build predictive models like lead scoring for sales leads. And so what Salesforce Einstein does is basically we want to inject this intelligence into the Salesforce experience for the companies so that they don't need to hire data scientists and data engineers to do it. Basically, what we do is we take the sales information, the service cloud information, running call centers, marketing information, all the social information, and when a company stores their data with us, we allow them to have machine learning apps built on top of that data, serving back scores that are customized to them so that they don't have to dedicate the resources to do it themselves. And as you can imagine, this is a pretty complicated problem, right? So if you think about your typical machine learning workflow as you might get from doing Kaggle competitions, you get some data and you do feature engineering. You build a model, you get a couple models that you think might work, and you do some model evaluation, right? And so this is sort of the very simple view of what you might do for machine learning. But if you talk about building a machine learning application where you're actually serving these numbers back to someone and not just building a toy, not building a proof of concept, this becomes much more complicated, right? So you have probably multiple sources of data coming in, and you do an ETL process in order to get those into some usable form. Then you do your feature engineering, model training, you get some models, and you evaluate that model. You decide to go back and try a couple of other models and evaluate again. You decide to go all the way back to feature engineering, and then maybe you decide that you need to do an entirely different evaluation in order to really get it. And then if you're lucky, you escape this loop and eventually go to deployment. And once you go to deployment, you need to bring your feature engineering back in order to do scoring, either in real time or in batch. And you need some sort of UI to actually make these numbers accessible and useful to people. So it's a long and complicated process to actually make this happen. And if you think about what I told you, that we have data from many different companies, this gets complicated, right? So let's say we have our first company coming and we want to build a data model for them. Basically, we can assign our first data scientist to do this. He may spend a couple months going through this process of ETL, modeling, evaluation. Eventually, he'll come up with something that's worthwhile, and maybe we'll deploy it. And then our next customer comes on, and he can start on that. He's had some learnings from the first model, so maybe he can cut some time off building the model for the second company that comes in. But again, we have our third company coming in and wanting this model while he's still occupied, so we need to hire another data scientist. He doesn't have the learnings from the first first situation, and so he needs to go back and start over, and he maybe comes up with a slightly different ETL process. I mean, you begin to see how this process doesn't scale to making models for hundreds and thousands of companies for even one application. So the example of something that we just launched GA is lead scoring for sales representatives. We need to be able to do this for hundreds of thousands of companies without involving data scientists, right? Because there aren't enough data scientists to do this. So the question might become, why not just do a global model? And it turns out there are a lot of good reasons why we can't do a global model. The first is privacy. So customers are entrusting us with their data. The number one priority for Salesforce is trust, right? Customers don't want their data to be used for their competitors' benefit. They want their data to be safe. They want only them to look at it. And the next is, of course, it doesn't actually make sense to combine the data. So business use cases for retail and banking, even for something as simple as lead scoring, are very, very different, right? The timelines are different, the closure rates are different, the processes are different. It doesn't actually make sense to try and build one model for these things across industries because they don't apply. The other issue is that Salesforce is actually a highly customizable platform. So customers can add columns to their data. They can add entirely new objects to their data. Basically, there is no guarantee that any particular column is being used the same way across two given customers, right? So you get this sort of wild card of data thrown at you, and it needs to be appropriate. You can't say that this particular column is going to have a weight across all customers because customers use those columns differently. And then the final point is that when you think about scaling and automation, hundreds of thousands of customers, some of which have millions or hundreds of millions of entities that they want scored, is actually a really big scale problem. And you're probably better off breaking it down and doing it individually in order to deal with that kind of scale. So we can't build a global model, which means that we're left with this problem, right? We need to do a machine learning workflow for each of our customers for any given application that we want to build. And remember that we want to build many applications. Each of those customers has a different scale. They might have a different process. They might have different columns. They have different distributions. And so we have to come up with a solution that allows us to build a good answer for each of these customers. And the way we do that is by automating a lot of our machine learning. So what this means, and we do this with an in-house library that we've built, which we call Optimus Prime. So what this means is that basically we're taking this black art that a lot of people think about as machine learning, where the data scientist goes, they tinker, and then eventually they come up with the right answer. Or if you read the XKCD, you stir the pile of data until the answers look right. You stir the linear algebra until the answers look right. But in reality, machine learning is not magic. It's just statistics. And there really is a process that data scientists go through in order to come up with those answers, right? So you look at the distribution of data. You do some data cleaning. You do some feature generation. You filter your data. You make the best features. And then you go ahead and select the right machine learning algorithm with the right hyperparameters in order to produce the best results. And so what we've done is really go ahead and make a system where the data scientist sort of sketches an outline of what this process would look like, and then the library goes ahead and tunes it to the individual data for each customer. And there were a couple of principles that we wanted to follow in creating this library. So we wanted to make it modular and reusable, and we wanted to use as much of what other people have built as possible. So I've given previous talks on this library, on a different version of this library that was built sort of at the same time as SparkML. It turns out that it's really hard to beat an open source library that has hundreds of contributors. And so this is actually, we've built a new version of this library that's on top of SparkML because we really like the abstraction that they had around estimators and transformers being put into pipelines. So basically, estimators are things that need to be fit to the data. They become transformers, which are essentially map operations, and then pipelines are used to string them all together. So we really like that abstraction. Some things that we didn't like were basically that there's no type safety in this. There's a lot of strings that pop up within data frames, which makes it problematic for production, particularly when your users can put whatever they want into the data, right? And so The other point is that we didn't want to be tied only to Spark ML algorithms. We wanted to be able to wrap other libraries when we wanted. And so basically, we came up with Optimus Prime, which was a way to do a sort of declarative and intuitive syntax. And we did this both for actually writing the code and, equally importantly, for developing. So we wanted a way for developers to contribute their own algorithms, their own wrappings, their own custom business logic very easily, because a lot of times that will sort of make or break the success of a machine learning algorithm. We did this with typed and reusable operations. And so the types actually really help ensure the reusability and make sure that things are used appropriately. And of course, we needed it to have this multi-tenant support. So we have to support customization, automatic customization across hundreds of thousands of tenants, making sure that the models and the features are done according to the distributions of the data and not according to some predetermined information that we might have, because we don't have predetermined information. And we chose Scala to build this basically because Scala is, one, the sort of first-class language in Spark, and it has a lot of sort of nice tricks for making all of this type safety happen. The other issue is sort of with Spark, and you think about Spark ML, it's really written so that it can have Python use cases, so that it can have Java use cases and Scala use cases. And in order to do that, they actually sacrifice some of the power of Scala. And so by focusing on just Scala, we were able to use a lot more of the language and really come up with sort of cleaner examples. And cleaner language. So our abstraction looks something like this. Essentially, we have these pieces. We have estimators and transformers, which are just stages. So again, these are like the Spark estimators and transformers. Basically, these estimators and transformers produce features, which can be transformed by stages, which again produce features. And you go ahead and do this until you've got the features you want, and then you materialize it with a workflow. The workflow knows where to get the data because you pass it in a reader. And with this abstraction, we can basically make a full machine learning pipeline with these 3 lines of code. So what we've got on the bottom here is a feature vector. Basically, these are a sequence of features. These are the features that you get as a raw data set from the Titanic data, which is sort of the classic machine learning example from Kaggle. You simply call a vectorize operation on that, which turns it into a feature vector. You can then check your feature vector against the label you're going to predict against, classify it against what you want to predict, and then materialize your final feature using a workflow and telling that workflow where to get the data with a reader. So how does the feature engineering on this work? Well, the key part here is really the features and the stages. So anytime you generate a feature with Optimus Prime, basically that feature has a type. And so this is a line of code that I emitted from my 3 magic lines. It can be auto-generated from your data. Basically, when you get your initial data, you give it a type, and you tell it what type the data is coming from. So this is the Titanic data set. We have a case class that represents that. You extract that data and tell it that it is categorical and it's a predictor. Each of these features is strongly typed, and each stage takes a specific input type and produces specific output types. So you can loop through with stages and features to create whatever you want for your DAG. And so what this looks like is something like this. Basically, the top row here is the raw features that you get from Titanic. And for each of these features, you may want to transform it into a new feature. You may want to basically pivot gender, extract the title from name, combine things into a feature vector, and then model it. And the type of those features determines which stages can actually run on them. So gender can be pivoted, and you'll get that as a tab completion in your editor because the type of gender categorical allows you to pivot. Similarly, name allows you to do a regex. Anything can be combined into a feature vector, and then you can model if you have a feature vector and a label, right? And I've shown modeling as the final step here, but Again, the model just produces more features. So if you wanted to feed the results of that model into another model, if you wanted to scale your model results, that's also possible. Basically, you can create any DAG you want. It's sort of similar to TensorFlow nodes in that it's very flexible in the way that you set up your DAG. And once you've found your final features, basically you're back to this abstraction. So you've got your final feature, you feed that into a workflow, tell your workflow where to get the data with a reader, and you can materialize things. So this is sort of the bare bones of it. But of course, I've just shown you sort of text and categorical. There's actually a lot more going on under the hood with the types, right? So I'm showing you this sort of magic line where we take all of our features and go vectorize. What's happening underneath the hood is that we're using type tags for each of those features to sort them into appropriate stages, right? So we know that basically categorical gender should be treated differently than a real number, such as age. And this will automatically happen with sort of best defaults for each feature type. But of course, you can go beyond that, right? So data scientists don't necessarily want our defaults, and they may want to inject some domain knowledge into what they're doing. And of course, we also allow that. So basically, if you know that age would be better treated as sort of relevant age buckets rather than a real number, you can do that with operations that are, again, type checked to be appropriate for that particular feature type. But you could do something like bucketize age. So you say, these are the age buckets that I want to put it in. It then returns basically a one-hot encoded vector of whether the age falls into each of those buckets. You can then pass that vector into your vectorized function. And since it's already a vector, it will just be concatenated with the results of the other features. So this allows sort of very specific manipulations as well as general default manipulations of feature engineering. And if you're not impressed by being able to treat categorical and real features differently, this is actually our feature hierarchy, right? And so this mirrors the Salesforce feature types. And what we've done is basically divided up features into many different types which inherit from each other. So we have text, which can go into email, phone, text area, which means a very large text field. We have numerics, which can be real, which might be percentage or currency. We have maps, we have sets, lists, including date lists, sort of a lot of detail about the particular features. And if you're a little bit horrified by this and think, why would you go ahead and make something like that? The answer is, well, first of all, a lot of times types are all you have in Salesforce. So I mentioned that customers can really change the data format on you. They can make their own custom objects. They can add their own fields. They can use fields differently within the same object. So sometimes the type of the object is really the only thing you know about it. It's the only thing you can use in order to do feature engineering. And the other benefit of this, and the reason that we've set it up as a hierarchy, is that by having both text and email, we basically have different levels of specificity that we can put on our stages. So there are specific transformations that are only appropriate for emails, and there are transformations that are appropriate for any kind of text feature, right? And so by having this hierarchy, we maximize code reuse by basically allowing our stages to be specified for different levels of type safety. And then again, as I mentioned, by having all of this type safety, which matches the Salesforce types, we ensure that end-to-end, we have type checks on our data, right? So when you're going into production with hundreds of thousands of customers who can change things on you, making sure that the type that the customer puts in is the same type that you're expecting in your model is really, really useful. And of course, we use it for more than just feature engineering. We also use it to check the data, right? So our customers might think that a particular field is very important. That's the field that they want you to model on. Turns out that they have a slightly different version of that field in another column that they didn't think to tell you about. This happens pretty frequently. And so we need to do things like sanity checking to look for label leakage, make sure that you don't have a model that looks perfect on paper, but when you try and deploy it is actually worthless because you're using data that's not there, right? And the other thing is that we can sort of check the ranges of features and allow the feature types to really specify what those checks are. So I know how you check whether or not a phone number is valid. I have no idea how you check whether or not text is valid. So basically, by having these very specific feature types, what we can do is really improve the checks on the data before we feed it into the model and filter out sort of invalid data before we go modeling. And that's done with this line on the bottom here. So we basically take our feature vector and then check it against the label that we're eventually going to predict on. Once we've done those checks, then we finally get to the stage that most people think of as AutoML, which is this model selection stage, right? And so you have things like hyperparameter tuning, checking different models. If your label is very sparse, you might want to do some resampling. And the idea is essentially that when you have many, many different customers with different sizes of data, with different distributions, the same model will not win for all of them. So if you're doing a classification problem, you may want to check logistic regression, random forest, naive Bayes, gradient-boosted trees, and make sure that you have the right hyperparameters for each of those models. And it turns out that even if random forest on average is the best model, it's not the best model in every single use case, right? Particularly for smaller data sets, logistic regression will often win. And so you really need to explore the space of models in order to get the best performance for each customer. And so what we've done is sort of combine this exploration into a single stage, sort of Uber stage, that's specified on the type of modeling that you're doing. So for instance, for classification, we will test many different models with many different hyperparameters and return the best one against the label that you're doing. Similarly, you could do this for regression. And so what we end up with is hopefully a very clean, performant model for each of our customers. And I hope at this point that I've convinced you that types are useful. If I haven't, then I'm going to make one last-ditch attempt and show you sort of a comparison of what this looks like in our code versus what this looks like in Spark code. So again, in Optimus Prime, you have your feature vector creation with a simple vectorize, and you then check your data and classify your data to produce the final features that you want, which are materialized with the workflow that's specified that gets the data from the reader. In order to do something like this for Spark, basically you would need to, with Spark, you would first need to specify different functions in order to do the data processing. So some of these are not standard Spark functions. You would then need to modify the data frame, so split it into test and training. You would need to prepare your categorical features. You would need to add all of your features together, put them together with a vector combiner. You would need to specify your logistic regression and tell it with strings, basically what the feature vector name is, what the label is, and feed that into your pipeline. Go ahead and build a parameter grid for your logistic regression to try some different hyperparameters, feed that into your cross-validation, and then eventually you get the model. And so what this leaves us with is basically this idea, and I'm going to quote my boss on this one, which is kind of weird, I know, and it's kind of a weird quote because he claims it's his 10th rule of machine learning. I don't know why it's the 10th, but that's what he says. I guess it's better than the 9th, it sounds better. But any sufficiently complicated machine learning code contains an ad hoc, informally specified, bug-ridden, and slow implementation of half of Optimus Prime. So I like that quote because it sounds good. And I think in general it's fairly true. So we've tried to automate a lot of what is done ad hoc in machine learning. So what do I hope that I have shown you here? Basically, machine learning for business to business is an entirely different beast than when you're thinking about consumer-facing machine learning, right? There's sort of a different scale, a different level of issues that come up. I hope that I've illustrated sort of that SparkML has some very nice abstractions around it, but type safety would really help it a lot. Simple, intuitive syntax is key. It saves you a lot of trouble down the road, increases code reusability. And if nothing else, I hope that I've convinced you that types will help you in machine learning. Scala has all of the relevant facilities to actually help you do this. I didn't delve a lot into how we actually made that simple syntax, but there's a lot of fun Scala magic underneath the hood. And of course, modularity and reusability are key. So by having everything set up into stages that are basically specified on type, you allow basically any stage that someone writes to be reused by other people as long as they have the appropriate types. So it really helps with code reuse. Sort of our next steps with Optimus Prime are really going beyond SparkML. So we have good wrapping of SparkML algorithms. We have easy ways for people to use anything that comes out in SparkML, so they can wrap it without us actually incorporating it into the library. They can move back and forth with SparkML, but we want to include algorithms from other libraries. So, for example, we've done some wrapping of Lucene. We want to move beyond that. We want to actually allow small-scale use as well. Of course, we have sort of a rough outline for everything that I've described here in terms of feature engineering, sanity checking, model selection. There's a lot that can be done to make it better. And for me, this is the really exciting thing. Like, this is the fun part of trying to figure out how to really improve all of this automation in machine learning. We want to do template generation, so the code that I showed you that I said could be auto-generated is not currently auto-generated, but should be. And so we want to basically have this feature where you say what type of modeling you're going to do, and you don't start with a blank slate. You start with an example of what this looks like. And so Prediction.io, if you're familiar with that project, had a really great example of sort of template generation for machine learning. They started you off with an example project, and we, well, Prediction.io was acqui-hired into my team, and we want to follow that model. And of course, we want to improve the developer interface so that it's easy for other people to use it. So if any of that sounds interesting to you, you should definitely contact us because we are hiring. We're also looking for companies to use Optimus Prime so that we can get feedback and maybe hopefully open source it. So if that sounds interesting to you, please talk to me afterwards. Thank you very much.
Thank you, Leah. We've got a few minutes for questions, so if you want to just raise your hand, I'll run over to you, and we can start the questions. There we go.
So this seems very interesting. Wondering whether you released any of these libraries to open?
No, we haven't released them. We're hoping to release them, but we need to get essentially 5 companies external to Salesforce to try them before we're allowed to open source them.
Okay, thank you.
Yeah.
Got another one over here.
Hi, great talk, and wouldn't take much to convince me that a lot of the types will have benefits even beyond what you've said. But some of what you showed seems like, I guess, a little bit of a trick. And what I mean by that is if you look at how much effort there was for Spark, it's because you had to specify a bunch of things. So by having types, it allows you to make more intelligent specifications, but only up to a point. You'll still have to probably put in just as much flexibility once you realize, oh, now I have the time, I can go back to specifying.
Yes, so that's true. So basically what I showed sort of the magic option, and we do have the sort of developer specified option, right? So you could go through and specify for each of those particular features the same level of basically stage control. So by having types, we allow good defaults. And so I did show that, basically the defaults that we showed. I showed the equivalent of those defaults in Spark, but it's true that you could manually specify basically those stages, and it wouldn't have been a 3-line comparison. It probably would have been 1 page versus 3 pages. So it's true that I did make it look better. But I think the tab completion and the specification are still cleaner with types.
Hi, thanks for the talk. So I'm working in a company right now where we're basically just doing machine learning applications for a specific purpose, but perhaps at some point in the future we'll be doing B2B. And me and my colleagues are trying to decide whether it's worth it to invest in the upfront cost of, I think he calls it a grammar, but I think basically what he means is type hierarchy. And so we're basically trying to decide when is it a good idea to add that level of abstraction. Do you think it's a good idea if we have only a very specific use case right now?
So, I mean, I think it's somewhere between 1 use case and 5, maybe. So the first machine learning model that you want to build, it's not worth it, right? That's definitely over-optimization. But once you start having a lot of models that are going into production, it definitely becomes worth it. I don't know where exactly you draw that line. It depends on how many data scientists are on your team, how much code reuse you want to have. It definitely helps with code reuse. So one of the things that I saw at LinkedIn was there were many sort of siloed teams doing machine learning, and they would repeat a lot of feature engineering. And it becomes much easier to share sort of modules when you have that type level. So I don't know, certainly if you just have one particular use case, it's not worth it. If you have 5, it may not be worth it. If you have 20, it's starting to become a good idea to have this sort of system in place.
Thanks.
All right, I think we're at time. If you have any more questions for Leah, she'll be at the front for a little bit. And thank you very much for your time.